Hi everyone, today I want to talk about an approach that learns a robot policy from imperfect demonstrations of different dynamics. Imagine you have a robot that wants to learn how to play basketball. We can always learn from professional basketball players, but it is often difficult to obtain large amounts of expert demonstrations. Instead, we sometimes have access to data from other professional sports like handball, or access to records of non-professional players like teenagers playing basketball. Our goal is to develop an imitation learning algorithm where the demonstrations may not be optimal. We might have perfect demonstrations from a robot with 3 degrees of freedom, optimal demonstrations from a robot with different dynamics such as an arm with 7 degrees of freedom, and suboptimal demonstrations. We use this mixture of demonstrations to learn a policy in our target environment. We formalize the problem of learning from imperfect demonstration as a MDP, the state space indicating the state of the agent, for example, the location and the velocity of the robot. The action space indicates what actions the agent can take. For example, the action indicates the rotation of joints. The reward function evaluates the reward at each step, given the state and action which is related to the task. For example, here we want to put the can on the table, so the reward can be defined as the negative distance of the can from the table. A policy is a function that maps a state to an action at each step, and the goal is to learn a policy that maximizes the total discounted reward. To start, let me first discuss 3 core imitation learning results. I will firstly introduce generative adversarial imitation learning, known as GAIL, as one possible way of learning from optimal demonstrations. I will then introduce 2 works for learning from non-optimal demonstrations, including both imperfect demonstrations and different dynamics. One common way of learning from optimal demonstrations is generative adversarial imitation learning. It uses the trajectories of the optimal demonstrations and the learning policy as input to the discriminator, and update the discriminator and the policy with a min-max gain. But GAIL requires the demonstration to be optimal and in the same dynamics as the target MTP. There is also work that is focused on learning from imperfect demonstrations. These works adopt a similar formula to GAIL but add a confidence weight here to model the optimality of demonstrations. Here, P theta is the distribution of the policy, Q is the distribution of demonstrations. To minimize the objective, the paper proposes 2 methods. The first method is to IWRL to directly learn a predictor to predict confidence. The second method is modeling R as a variable and learn R with the discriminator and the policy simultaneously. However, both methods require demonstrations to be in the same dynamics as the target MDP. We then review the work on learning from demonstrations with different dynamics. Data-aligned-based imitation learning aims to learn a policy from demonstrations provided by an agent with different dynamics. The key insight is that when the state of the imitator deviates from the demonstration, if imitating the state transition, the action can be recovered by the inverse dynamics of the imitator. Then the imitator and the robot can match at the next state. But if we try to imitate both states and actions, the next state can even deviate more. So this work imitates state sequences and recovers the actions through unknown inverse dynamics. However, SEAL requires the demonstration to be perfectly optimal in a different dynamics. The prior works either focus on the imperfect demonstrations or demonstrations from different dynamics. Recall that our setting allows that the demonstrations are imperfect demonstrations from agents with different dynamics, so prior works cannot deal with our problem setting. Given the demonstrations, our feasibility score indicates the likelihood that a demonstration trajectory is achievable in the target environment, and we develop an optimality score that indicates the optimality of a trajectory. We then consider a final weight which is the product of feasibility and optimality, and sample demonstrations from the distribution defined by W to train any imitation learning algorithm and learn an optimal policy. Let us first discuss the feasibility of a given demonstration. First, for a given demonstration, for example, the one shown in the red, we want to generate a corresponding trajectory in the target environment shown in the blue with the same initial state as the red demonstration. Given the initial state in blue and the next state from the demonstration, we generate an action by the inverse dynamics of the target agent. This action most closely recovers the next state in the demonstration. Then we execute this action in the target environment to get to the next state. We repeat this process until we generate the same number of steps in the corresponding trajectory as the original demonstration. We compute the feasibility based on the distance of the states at each step. You can imagine for a feasible trajectory, all the state transitions in the demonstration can be recovered, so the distance d is 0, but when the trajectory is infeasible, the distance is larger than 0. However, when the inverse dynamics model is not optimal, even the feasible trajectories have larger than 0 distance. We set a threshold d min to be the minimum distance d among all the feasible trajectories as a lower bound for distance d. Distances lower than d min are mostly feasible trajectories. Similarly, we set an upper bound for the feasibility metric as the tolerance for a trajectory with positive feasibility. We set dmax by perturbing the states of all the feasible trajectories. Here, you can see we have the action and we generate the expected next states. Then we perturb it to another state, and we go back to the next action, and we get the next state, and then we also perturb the next state, and we generate a corresponding trajectory. After that, we get dmax by the maximal distance between all the feasibility trajectories and the corresponding trajectories. Any trajectory with distance higher than dmax is regarded as totally infeasible. We can then define the feasibility by setting the distance lower than d min as 1, setting distance between d min and dmax to be between 0 and 1, and setting distance higher than dmax as 0. The feasibility can filter out far from feasible trajectories but still preserve some nearly feasible trajectories for learning. Now that we have discussed how to find the feasibility score, we would like to next talk about computing the optimality score. One key insight is that we need to access the optimality based on the reward and further make the optimality agnostic to the choice of initial states. Prior work models optimality by a confidence weight based on the dynamics of the demonstrations. However, such an optimality score does not work when demonstrations are from different dynamics. As an example, we have an agent who wants to reach the original goal area. We define 3 dynamics based on the turning ability of the agent. One is unlimited turns, the second is that no turns are allowed, and the third is the agent is only able to turn in half-pi increments. We show the optimal trajectories for the 3 dynamics in red, green, and blue color respectively. This example demonstrates that the optimal trajectory in one dynamics may not be optimal in another dynamics. Like the green trajectory will not be optimal when you can have unlimited turns. Therefore, we need a measure that can be used across dynamics. So here we use the reward of trajectories as they are only state dependent and do not vary when dynamics change. Using only the reward values as an optimal measure is not enough. In this example, we can observe that all the trajectories are optimal with respect to their initial states. But if we use the reward as an optimality score, then trajectories 2 and 3 will be preferred by this measure. However, this optimality metric will discuss important information from trajectories 1 and 4, so our notion of optimality needs to be agnostic to the choice of the initial state. So we define a rectifying function at each initial state as the maximum reward for trajectories starting from this initial state. We estimate the rectifying function from nearby initial states. Here in all demonstrations, we find feasible demonstrations with nearby initial states. and use the maximum reward in these trajectories. We then define the optimality as the negative distance between the trajectory reward and the maximum reward. Now that we have both feasibility and optimality scores, we can perform imitation learning by sampling demonstrations based on the score defined by the product of feasibility and optimality. Then we introduce our experiments to evaluate our method. We conduct experiments on different environments, and in each environment we define two different dynamics. In the majorcal ritual environment, we define clockwise and counterclockwise movement of the ritual agent as the two dynamics. We train on a mixture of imperfect demonstrations of different dynamics and test in each environment. We conduct experiments comparing with baseline methods with no weights, as well as other baselines such as 2IWRL and ICRA and SAIL. We also compare our algorithm with variants of our method, including using a naive version of optimality and only using the feasibility score. Our algorithm outperforms all the baselines in the ritual environment in majorcal. We see similar results when the targeting environment is the counterclockwise domain. The second environment we experiment with is the majorcal swimmer environment with the front and back joint disabled. We see similar results when comparing with our algorithm with the baselines. Also similar for front disabled. Finally, we conduct an experiment on the real robot to put an apple down on the table without hitting obstacles. We compare our results with only using feasibility or only using optimality, and our algorithm outperforms these baselines as shown in the video. In summary, our approach learns from suboptimal demonstrations with varying dynamics by capturing a feasibility and optimality score to assess the informativeness of imperfect demonstrations.